So this question, you have a dice manufacturer and they make novelty dice, and the probabilities for 1 to 5 are all equal, but 6 is 2 times more likely to come up. So we need to find the probability of scoring a 6 when we roll this dice. So this is the, So this is the first part of the question, part A. And we know that each of the probabilities from 1 to 5 are the same. So if I think about it as a score and the probability that that score happens, I can get 1, 2, 3, 4, 5, or 6 on my dice. And the probability of that happening is the same for each of the numbers 1 to 5 and double that for the last one. So that means in total, I know that all probabilities have to total to make 1. So 7x equals 1, and therefore x is equal to 1 over 7. So the probability of scoring a 6 on the novelty dice, the probability of a 6 is going to be 2 out of 7, okay, if x is 1 over 7 and I've got 2 of them. So this is 1/7, 1/7, 1/7, 1/7, and then the last one there, 2/7. So part B is find the probability of scoring more than 2 6s when the dice is rolled 5 times. So this is actually a binomial question, and we know that x is the probability of scoring a 6. It's binomial. I roll it 5 times, and the probability of rolling a 6 is 2/7. I'm asked to work out what's the probability that x is bigger than 2, which means that I score more than 2 6s, not equal to, but more than. If I'm rolling it 5 times, I could get 0 6s, 1 6, 2 6s, 3 6s, 4 6s, or 6 6s. No, hold on, 5 6s, sorry. I'm rolling it 5 times. I'm interested in more than 2 times. So I'm interested in 3, 4, or 5 times. So when I type it into my calculator, I need to do 1 minus, and then it's the probability that x is less than or equal to 2. Okay, so I'm now going to go to my calculator, and it's distributions. I'm interested in the binomial distribution, and it's CDF. It's 5 different trials, and it's 2/7 as my probability of success. So I can do that as 2 over 7, and I am interested in x is less than or equal to 2, as I've just written here. So that gives me 0.855. So 1 minus that answer. So 1 minus this, and I get 0.1, and it's 4/5. And then part C, I need to find the expected frequency for each of the numbers. So they've tested this claim by rolling it 350 times, and we're trying to see if it fits what we would expect to happen so that we can do this chi-squared goodness of fit. So what we would expect to happen is 1/7, using those probabilities I found earlier, as to have scored a 1. So for the expected values for 1, 2, 3, 4, 5, and 6, we would expect of 350 times, 1/7 of them to be 50. So each of these would be 50, and then the probability of rolling of 6 is double, so we would expect to see a double, which is 100. So that's part C, part 1. And then C, part 2 is to write down the null and the alternative hypothesis. So for the null hypothesis, it's always like what we expect to happen. So the null hypothesis here, this is part 1. Part 2 is the manufacturer's claim is going to be correct, basically. So the claim, manufacturer, you should probably write the claim is correct. And then for the alternate hypothesis, this is what we're testing to see because we're doubtful, and that's that the manufacturer's claim is incorrect or is wrong, not correct, however you want to say that. Part C and then part 3 is then to state the number of degrees of freedom. So the degrees of freedom are 5. It's always 1 less than the data we have, and we have 1, 2, 3, 4, 5, 6 pieces of data, and therefore it is 1 minus that, which is 5. And then for the last part, we want to complete the chi-squared goodness of fit test to find the p-value, and then we can determine what the outcome of the test is. So we're going to go across to the data. We need to type in the expected and the observed data. So the observed data is 32, 57, 47, 58, 54, and 102. And what we were expecting to see is 50 for each value, but 100. Oops. Here we go. Sorry, 50 for all of them and 100 for the last one. So we can now go across to our tests, and we want the chi-squared goodness of fit. The observed data is in the first list, the expected is in the second list, and the degrees of freedom are 5. And then from this, we find that the p-value is 9.84%. So the p-value is 0.0984, which is 9.84%. And therefore, since our p-value is greater than our significance level, which is 5%, so this is 5%, this is 9.84%, therefore, we accept H0. Okay, which means that the manufacturer's claim is correct, and actually it's a pretty good novelty dice that seems to follow what they're expecting it to follow. So in terms of the marks for this one, the first part of the question is 3 marks. So those 3 marks are for some sort of method for showing that you understood what the process was, 1 for finding the value of x, and then 2 for finding and presented the probability of 6. Part B is 4 marks. So for those 4 marks, 1 is for recognizing that it is binomial. The second is for correctly recognizing that it's binomial. So for writing something like this. The third one is for recognizing that you needed to use the CDF and for subtracting, or if not, for working out 0, 1, and 2 and then adding them together. And then there is a final mark there at the end for your final answer of 0.145. Part C, so the first part is 2 marks, and that is for finding the expected frequency. Yeah, so that's 2 marks for this, and it's just 2 marks given in total. You can't get 1 mark and 1 mark, it's just 2 marks. The Second part also 2 marks, and this is for correctly identifying each of the hypotheses. Then there's 1 mark for finding the degree of freedom is 5. 2 marks, again, cannot be separated out, which is for finding the p-value and rounding it correctly. So if you rounded it incorrectly, you lose both marks. And then at the end there, you have a reasoning mark and an answer, and you can't have the answer without the reason, and you can't have a reason without an answer. So essentially they come as a pair.